Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is flow rate and actuator speed. Our objective is to learn how flow rate and volume influence actuation time and speed for linear actuators like hydraulic cylinders. Additionally, we'll examine the relationship of displacement, rotational speed, and flow rate for pumps and rotational actuators like hydraulic motors. This lecture operates under the presumption the viewer has watched the circular area and cylindrical volume lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only demo recall its contents, please take the time to do so now. A word of warning to the viewer. The scope of this lecture is limited to hydraulic systems, i.e. fluid power systems that use incompressible liquids like oil to transfer power. The incompressible nature of liquids means a given volume of liquid remains that exact same volume regardless of pressure conditions. For example, 1 gallon of oil at 10 psi still occupies exactly 1 gallon of volume at 100 psi or 1,000 psi, or even 10,000 psi. Now, this is not true, especially at extremely high pressures. However, for the purposes of this lecture series, we are going to assume it is. The incompressible nature of liquids makes flow rate and actuator speed calculations extremely easy. Pneumatic systems, i.e. fluid power systems that use compressible gases like air to transfer power, in contrast, aren't nearly as easy to calculate these same properties since a given quantity of air occupies different volumes at different pressure and temperature conditions. For example, a standard cubic foot of air occupies a cube 12 inches by 12 inches by 12 inches or 1,728 cubic inches at 68 degrees Fahrenheit at sea level atmospheric conditions, but only 864 cubic inches, being a cube roughly 9.5 inches by 9.5 inches by 9.5 inches at twice atmospheric pressure at 68 degrees Fahrenheit. To further complicate matters, compressible gases like air are additionally subject to temperature-induced changes in volume and pressure. We'll examine the behavior of ideal gases and pneumatic systems in much later lectures. Again, this lecture is limited to scope to hydraulic systems, i.e. fluid power systems that use incompressible liquids like oil to transfer power. Let us begin. First, let's refresh our understanding of unit conversion, circular area, and cylindrical volume. 1 gallon is equivalent to 231 cubic inches. Don't ask me why, I don't know. If we wanted to convert a given quantity of gallons, let's say 4.5 gallons to cubic inches, one would multiply 4.5 gallons times 231 cubic inches over 1 gallon such that the unit we don't want, gallons, cancels out, and the unit we do want, cubic inches, remains. This calculation demonstrates 4.5 gallons is roughly equivalent to 1,039.5 cubic inches. This additionally serves as a reminder that U.S. customary units like gallons and cubic inches do not use engineering prefixes, and this quantity cannot be expressed as 1.0395 kilocubic inches and must be expressed in its awkward entirety. We can also do this conversion in reverse. If we wanted to convert a given quantity of cubic inches, let's say 115.5 cubic inches to gallons, one would multiply 115.5 cubic inches times 1 gallon over 231 cubic inches such that the unit we don't want, cubic inches, cancels out and the unit we do want, gallons, remains. This calculation demonstrates 115.5 cubic inches is equal to 0.5 gallons. This additionally serves as a reminder that U.S. customary units like gallons and cubic inches do not use engineering prefixes, and this quantity cannot be expressed as 500 milligallons and must be expressed in its awkward entirety. The viewer should additionally be able to calculate the cap and rod end area and volume of a double-acting hydraulic cylinder. Consider a double-acting hydraulic cylinder with the following dimensions: diameter of cap 4.5 inches, diameter of the rod 1.25 inches, and a travel length of 18 inches. An application of the circular area formula demonstrates the fully circular cap end has an area of roughly 15.9 square inches. An application of the cylindrical volume formula demonstrates the fully cylindrical cap end has a volume of roughly 286.3 cubic inches at full extension. Another application of the circular area formula demonstrates the smaller rod has an area of roughly 1.2 square inches. The area of the ring-like rod end is the area of the cap minus the area of the rod. Substituting our calculated values demonstrates the ring-like rod end area has an area of roughly 14.7 square inches. The volume of the tube-like rod end is the area of the ring-like rod end times the height. Substituting our calculated values demonstrates the tube-like rod end has a volume of roughly 264.2 cubic inches at full retraction. You will note that the tubular rod end has less volume than the fully cylindrical cap end because the solid rod, when fully retracted, occupies that space. This will have consequences when it comes to calculating actuator speed, as we'll soon demonstrate. All right, hopefully these techniques were a review. If not, please check out the aforementioned lecture and bring yourself up to speed. Let's now move on to the topic of today's lecture, flow rate. Flow rate is a measure of how fast or slow a volume is occupied. Flow rate is customarily measured in units of gallons per minute, abbreviated as GPM, or if you're in a country with a working government and a functional healthcare system, liters per minute, abbreviated as LPM. Both of these are measurements of units of volume per unit time. I say again, flow rate in units of GPM is a unit of volume, the gallon, per unit of time, the minute. This directly specifies how to calculate flow rate. Flow rate, Q, don't ask me why it's Q, I don't know, is measured in gallons per minute, is volume in units of gallons divided by time in units of minutes. Q equals V over T. An extremely convenient way of graphically expressing this three-variable relationship is using a three-variable pyramid, with volume at the apex and flow rate Q and time T side by side forming the base. To solve for Q, take volume V and divide it by time T because flow rate is volume over time. To solve for volume V, take flow rate Q and multiply it by time T because they're side by side. Finally, to solve for time T, take volume V and divide it by flow rate Q because volume is over flow rate. As simple as this three-variable relationship may seem, it is not without its complications, principally because a user often has to deal with unwieldy and archaic unit conversions commonplace in the fluid power industry. Consider our previous area in volume calculations involving a double-acting hydraulic cylinder, notably a cylinder having the following dimensions: cap diameter of 4.5 inches, a rod diameter of 1.25 inches, and a travel length of 18 inches. Using our previously acquired knowledge of circular area and cylindrical volume, we demonstrated the fully circular cap has an area of 15.9 square inches, and at full extension, the volume of the fully cylindrical cap end is 286.3 cubic inches. Let's deal strictly with the act of extension first. Extension necessitates oil enter the cap end port and fill the fully cylindrical cap end. Only when 286.3 cubic inches has filled the space will this cylinder fully extend the 18-inch rod. The act of extension also implies that the rod end is simultaneously evacuated. Let's say the cylinder is subjected to a flow rate of 2.2 gallons per minute. And again, we're being asked to solve for the extension time. Simple, right? You got a known volume and a known flow rate. Time is just volume over flow rate. Away we go. Hold on, not exactly. Pay attention to the units. As simple as this setup is, a known volume in cubic inches and a known flow rate in gallons per minute, our volume units don't match. Additionally, is a minute really the best choice of time? For this application, probably not. Think about it. If a gallon is 231 cubic inches and the fully cylindrical cap end has a volume of 286.3 cubic inches, it's a little bit more than a gallon. If you got a flow rate of 2.2 gallons per minute, or around 2 gallons per minute, most likely this space is going to take less than a minute to fill. It's for this reason I highly recommend a user first convert flow rates in gallons per minute to a more usable format, notably cubic inches per second. This necessitates a chain of conversion. First, change gallons per minute to cubic inches per minute, then cubic inches per minute to cubic inches per second. To do so, one multiplies 2.2 gallons per minute times 231 cubic inches over 1 gallon, such that the unit we don't want, gallons, cancels out, and the unit we do want, cubic inches, remains. This first stage of the unit conversion demonstrates 2.2 gallons per minute is equivalent to 508.2 cubic inches per minute. Next, we convert cubic inches per minute to cubic inches per second. To do so, one multiplies 508.2 cubic inches per minute times 1 minute over 60 seconds, such that the unit we don't want, minutes, cancels out, and the unit we do want, seconds, remains. This final stage of the unit conversion demonstrates 2.2 gallons per minute is equivalent to 508.2 cubic inches per minute, which is also equivalent to 8.47 cubic inches per second. By the way, you may see flow rate in units of cubic inches per minute expressed using the abbreviation CIM, as in cubic C, inches I, per minute M, and flow rate in cubic inches per second expressed using the abbreviation CIS, as in cubic C, inches I, per second S. Having completed this necessary first step, we are now set up for a quick and easy flow, volume, and time calculation. Time is volume over flow rate. Substituting our calculated values for the volume of the cap end in units of cubic inches and flow rate in units of cubic inches per second demonstrates this cylinder should reach full extension in roughly 33.8 seconds. Before we move on to the act of retraction, think about the extension speed of this cylinder. Again, be careful with the units. Speed is a measurement of length per unit time. What speed units do you want? Inches per second, feet per minute, miles per hour? The point being, you may have to perform an additional unit conversion depending upon the desired units. If you want extension speed in units of inches per second, we are already set up for success. Speed is length per time. The rod moved 18 inches in 33.8 seconds, achieving a speed of roughly 0.532 inches per second. Slow indeed, but still faster than your lazy lab partner. If, however, we're asked to determine the speed in some other unit, let's say feet per minute, one again necessitates a chain of conversion. First, change inches per second to inches per minute, then inches per minute to feet per minute. To do so, one multiplies 0.532 inches per second times 60 seconds over 1 minute, such that the unit we don't want, seconds, cancels out, and the unit we do want, minutes, remains. First stage of the unit conversion demonstrates that 0.532 inches per second is roughly equivalent to 32 inches per minute. Next, we need to convert inches per minute to feet per minute. To do so, one multiplies 32 inches per minute times 1 foot over 12 inches, such that the unit we don't want, inches, cancels out, and the unit we do want, feet, remains. This final stage of the unit conversion demonstrates the cylinder extends at roughly 2.7 feet per minute. If you think about it, flow rate, volume, and time calculations are super easy. After all, it's just 3 variables. Any difficulty you may encounter with these types of calculations simply may be because of unit conversions. My advice is this: stay neat, stay organized. A task which may be beyond your lab partner's capacity. Above all, do your results make sense? In this case, they certainly do. We're presented with a volume of a little bit more than a gallon and a flow rate of a little bit more than 2 gallons per minute. Is it surprising it takes around half a minute to fill? No, it is not. Given it took roughly half a minute to extend, 1.5 feet, is it surprising the rod is moving around 3 feet per minute? Again, no, it's not. The point being, have a rough idea of the results before you do the calculation. In later lectures, we'll examine pumps, flow control valves, and different flow control methods that can vary the flow rate into or out of an actuator and thus vary its actuation speed. For now, consider this simple thought experiment. What happens if I increase flow rate? Too easy. Actuation time is V over T. If Q rate is increased, actuation time should decrease. It makes sense. More units of volume are being stuffed into a constant volume at a faster rate, thus the time it takes to fill it decreases. Less actuation time means the actuator moves faster. Conversely, what happens if I decrease flow rate? Again, too easy. Actuation time is V over Q. If Q is decreased, actuation time should increase. Again, it makes sense. Less units of volume are being stuffed into a constant volume at a slower rate, thus the time it takes to fill increases. More actuation time means the actuator moves slower. Lastly, consider the influence of volume on actuation speed. Given a constant flow rate, larger volumes take more time to fill, whereas at a constant flow rate, smaller volumes take less time to fill. It all makes sense. Case in point, consider the act of retraction for this same double-acting cylinder. The act of retraction necessitates the smaller tube-like volume of the rod end be filled, while simultaneously the volume of the cap end is exhausted at low pressure. During the act of retraction, a solid steel rod is pulled into the rod end, which occupies space, thus displacing oil entering the rod end. Long story short, the tubular rod end volume necessitates less oil volume be filled than the fully cylindrical cap end. Again, consider a constant 2.2 gallons per minute of flow entering the rod end and answer this simple multiple choice question. No calculations required. The time to fully retract this cylinder will be blank as the time to fully extend the cylinder. A, less than, B, more than, C, the same as, D, none of the above, E, all of the above, and F, yes. If you said the time to retract will be A, less than the time to extend, you are correct. In fact, this answer is always correct, all the time, every time, in all scenarios, and never forget it. If you have a constant flow rate and less volume to fill, actuation time will always be less. At constant flow rates, double acting cylinders retract faster than they extend because they've got less volume to fill. Let's prove it. As we previously demonstrated, 2.2 gallons per minute is equivalent to 8.47 cubic inches per second. The volume of the tubular rod end at full retraction is roughly 264.2 cubic inches. Time is volume over flow rate. Substituting in our calculated values for the volume of the rod end in units of cubic inches and flow rate in units of cubic inches per second demonstrates the cylinder should fully retract in roughly 31.2 seconds. What did I tell you? At a constant flow rate, reaction time is less than extension because there's less volume to fill. Using techniques as previously, one can also calculate retraction speed in either inches per second or feet per minute. Speed is length per time. The rod retracted 18 inches in 31.2 seconds, achieving a speed of roughly 0.577 inches per second. To convert this quantity to feet per minute necessitates a chain of conversion. First change inches per second to inches per minute, then inches per minute to feet per minute. To do so, one multiplies 0.577 inches per second times 60 seconds over 1 minute, such that the unit we don't want, seconds, cancels out, and the unit we do want, minutes, remain. This first stage of the unit conversion demonstrates that 0.532 inches per second is roughly equivalent to 34.6 inches per minute. Next, we need to convert inches per minute to feet per minute. To do so, one multiplies 34.6 inches per minute times 1 foot over 12 inches, such that the unit we don't want, inches, cancels out, and the unit we do want, feet, remains. The final stage of the unit conversion demonstrates this cylinder extends at roughly 2.9 feet per minute. Like I said, at a constant flow rate, retraction always occurs faster than extension because there's less volume to fill. Before we move on to discuss pumps and rotating hydraulic actuators, let's see if you're tracking with this illustrated example problem. Consider a double-acting hydraulic cylinder with the following dimensions: diameter cap of 6 inches, diameter rod of 2.5 inches, a travel length of 24 inches. Let's say the cylinder is subjected to a constant flow rate of 8 gallons per minute. See if you can solve for the time of extension, units of seconds, and the speed of extension, units of inches per second and feet per minute. Extension necessitates liquid completely fill the fully cylindrical cap end. Additionally, see if you can solve for the time of retraction in units of seconds and the speed of retraction in units of inches per second and feet per minute. Retraction necessitates liquid completely fill the tubular rod end. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The fully circular cap has an area of 28.3 square inches, and at full extension, the volume of the fully cylindrical cap end is 678.6 cubic inches. The ring-like annular rod end has an effective area of roughly 23.4 square inches, and the tubular rod end at full retraction has a volume of roughly 560.8 cubic inches. A chain unit conversion demonstrates 8 gallons per minute is equivalent to 1,848 cubic inches per minute, which is equivalent to 30.8 cubic inches per second. Extension necessitates liquid completely fill the fully cylindrical cap end. Extension time is the volume of the cap end divided by a flow rate. This yields an extension time of roughly 22 seconds. The rod moved 24 inches in 22 seconds, or around 1.1 inches per second. This corresponds to a speed of roughly 5.4 feet per minute. Retraction necessitates liquid completely fill the tubular rod end. Retraction time is the volume of the rod end divided by a flow rate. This yields a retraction time of roughly 18.2 seconds. As one might expect, retraction occurs faster at the same flow rate because there's less volume to fill. Lastly, the rod retracted 24 inches in 18.2 seconds, or around 1.32 inches per second. This corresponds to a speed of roughly 6.6 feet per minute. All right, that wasn't too hard, was it? Let's now have a quick discussion about pumps and rotational hydraulic actuators, like hydraulic motors, before we bring this lecture to a close. As you're no doubt aware, a pump is a device that converts the rotating mechanical power of some prime mover, be it an electric motor or an internal combustion engine, to fluid power. Two aspects define fluid power: pressure and flow. We'll examine pressure, Pascal's law, and pumps in greater detail in later lectures. This lecture restricts itself to flow. A common pump property is that of displacement, which is a measure of volume per revolution, meaning every time a pump shaft is turned one full revolution, it introduces that much volume into a hydraulic system. Consider a pump with a displacement of, let's say, 0.5 cubic inches per revolution, where one might encounter this displacement property on a pump data sheet written as CIR, as in C cubic, inches I, R revolution. To yield a usable flow rate, i.e. a volume per unit time, one needs to know at what rotational speed the pump is being driven at. The property of rotational speed is often expressed as N. Again, don't ask me why it's N, I don't know. And it's measured in units of revolutions per minute, or RPM. To yield a flow rate, one multiplies displacement per revolution times revolutions per minute. Q equals D times N. Units of revolutions cancel out, and you'll be left with a unit of volume over time, i.e. a flow rate. Again, consider a pump with a displacement of 0.5 cubic inches per revolution being driven at a rotational speed of 1,780 revolutions per minute. What's the flow rate? Now, before you screw this up, listen carefully. What's the flow rate in gallons per minute? Multiply 0.5 cubic inches per revolution times 1,780 revolutions per minute. Revolutions cancel out, which yields a flow rate of 890 cubic inches per minute, which again might be expressed as CIM. This is not the answer we're looking for. We need to convert this to gallons per minute. To do so, one multiplies 890 cubic inches per minute times 1 gallon over 231 cubic inches, such the unit we don't want, cubic inches, cancels out, and unit we do want, gallons, remains. This yields a flow rate of roughly 3.9 gallons per minute. Again, flow rate calculations shouldn't be that hard. Any difficulty you have with this topic may be because of unit conversions. Stay neat, stay organized. You note two properties influence flow rate output of pumps, noticeably displacement per revolution and revolutions per minute. This implies pumps can vary their flow rate output by varying one or both of these properties. As we'll learn in later lectures, there exist fixed and variable displacement pumps. A simple, inexpensive, fixed displacement pump always outputs the same volume per revolution, and as the name implies, displacement is invariable. In contrast, a more sophisticated and coincidentally more expensive variable displacement pump has movable internal components that can increase or decrease displacement per revolution to meet flow requirements. Increased displacement per revolution means more flow rate at a given rotational speed. In contrast, decreased displacement per revolution means less flow rate at a given rotational speed. Another simple method can be used to vary flow rate even for fixed displacement pumps. All you got to do is just drive them faster or slower to meet flow requirements. Increased rotational speed means more flow rate at a given displacement. In contrast, decreased rotational speed means less flow rate at a given displacement. In much later lectures, we'll examine a power electronics device known as an inverter that can vary the output voltage magnitude and frequency to a motor under its direction, thus changing the motor prime mover and the pump's driven speed to vary flow rate. Lastly, do not labor under the mistaken impression that the property of displacement per revolution is a fixed and ever constant value, even for fixed displacement pumps. The displacement figure specified on a pump's datasheet is a single snapshot at a single operating condition known as the rated condition, i.e., what the pump has been designed to do. If the pump is being driven in excess or below its rated condition, one might expect displacement per revolution to vary. For example, let's say a hydraulic system is exerting a lot of force and necessitates super high pressures. At extremely high pressures, one might expect displacement per revolution to drop because of increased leakage. As if that wasn't enough, at super high pressures, the prime mover driving the pump may experience more load torque, and the resultant rotational speed may also slow down. The combined effects of reduced displacement per revolution because of leakage and decreased rotational speed of the pump because of increased torque requirements, obviously being that flow rate understandably decreases, and decreases at higher pressures. We'll examine pumps and motors in later lectures. Lastly, I should mention hydraulic actuators are not limited to linearly acting single and double acting hydraulic cylinders. There also exist rotational hydraulic actuators known as hydraulic motors, which I like to think of as anti-pumps. A pump is a device that converts rotational mechanical power into fluid power. In contrast, a hydraulic motor converts fluid power into rotational mechanical power. Even their schematic symbols are opposites. The schematic symbol of a pump shows an arrow pointing away from the pump into the hydraulic system. In contrast, the schematic symbol of a hydraulic motor shows arrows pointing into the motor from the hydraulic system. Two arrows indicate the motor is bidirectional, meaning it can rotate clockwise or anti-clockwise depending on direction of fluid flow. Similar to pumps, hydraulic motors also have a displacement figure specified in volume per revolution. Only this figure means it necessitates that much volume be introduced by a pump for the motor to turn one full revolution. To calculate the resultant rotational speed output of a motor in units of RPM, one would divide flow rate by displacement per revolution. N equals Q over D. Again, be careful of this arrangement. As simple as this formula seems, it is not without its traps. Displacement is often specified in CIR, which if you remember right, stands for cubic inches per revolution, whereas Q, flow rate, is often specified in gallons per minute. There's a mismatch in volume units, and you need to find some commonality. Although there exist other equally valid methods, my sincere advice is to convert Q in units of gallons per minute to cubic inches per minute before you attempt these calculations. For example, consider the previous pump with a displacement of 0.5 cubic inches per revolution being rotated at 1780 RPM. As we previously demonstrated, this results in a flow rate of roughly 3.9 gallons per minute. What if this pump output was being used to drive a bidirectional hydraulic motor with a large displacement of 4 cubic inches per revolution? What is the output rotational speed of the hydraulic motor shaft? As we previously demonstrated, 3.9 gallons per minute is equal to 890 cubic inches per minute. Rotational speed is flow rate divided by displacement. This yields a rotational speed of roughly 222.5 revolutions per minute. Pause to consider what's going on here. Some of you might be like, big deal. You got an electric motor turning a pump, which in turn, pardon the pun, turns a hydraulic motor. Why are you going all this trouble when the electric motor itself is a rotational actuator? Why not just use the electric motor to directly drive the load? Check it out. Given the pump and hydraulic motor have different displacements per revolution, this system is essentially acting as a fluid-based step-down gearbox for the electric motor prime mover. We'll examine rotating mechanical power in greater detail in later lectures, but as a preview, mechanical power is a product of twisting force called torque, T, and rotational speed divided by a constant. It's obviously too much to ask of the real world, but consider a 100% efficient system where 100% of the high-speed, low-torque mechanical power output of the electric motor prime mover is converted into hydraulic power with a given pressure and flow rate by the pump, and then the hydraulic motor converts 100% of the supplied hydraulic power to low-speed, high-torque rotating mechanical power. Can you dig it now? A small displacement pump being driven at a super fast speed yields a slower moving rotational actuator with significantly more torque. This forms the basis of a number of hydraulic devices, a common example being a hydraulically driven winch used to extract a mired vehicle with a low-speed, high-torque hydraulic motor. All right, before I cut you loose, try this quick illustrated example problem on for size. Consider a fixed displacement pump with a displacement of 0.6 CIR, or cubic inches per revolution, being driven at 1760 RPM. This pump is driving a hydraulic motor with a displacement of 0.832 CIR. So if you can determine the flow rate in units of gallons per minute and the rotational speed of the hydraulic motor in units of RPM. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following results. Flow rate is the displacement of the pump times the rotational speed of the pump, which yields 1,056 cubic inches per minute, which is equivalent to 4.6 gallons per minute. Lastly, the rotational speed of the motor is flow rate in cubic inches per minute divided by the displacement of the motor. This yields 1,272.3 RPM. All right, that's all I got for you for this lecture. In conclusion, this lecture introduced the relation of flow rate, volume, and time for hydraulic systems. Additionally, we learned to calculate extension and retraction times and speeds for linear hydraulic cylinders. Lastly, we examined flow rate, displacement, and rotational speed calculations for pumps and rotating hydraulic actuators like hydraulic motors. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.